Good morning, everybody, and thank you for joining us today for this webinar on hydrogen deblending. I'm Tom Collar, the Programme Lead for Gas Goes Green at Energy Networks Association. Gas Goes Green is the network programme, a joint initiative supported by Britain's 5 gas network companies, National Grid, Cadent, Northern Gas Networks, SGN and Wales and West Utilities, many of which you'll hear from today. And we're excited to be with you today to discuss hydrogen deblending, the opportunities it may bring, and how it could enable and accelerate the hydrogen transformation. Before I pass to Tony Green for his welcoming introduction, a couple of housekeeping matters. Questions. So we really want your questions. We put together an excellent array of experts who you'll hear from, but we know that we have an audience of industry experts as well. So we've set up Slido so you can ask your questions at any time, rate and rank other people's questions. And we've got several Q&A sessions coming up where as many of these as possible will be answered and discussed. So please, if you've not already got the page up ready, go to slido.com or sli.do on your web browser or download the app and enter the event code. It's in the top left of your screen there, GGG02. We have some questions later on in the session which we'll be asking you, but you can ask your questions at any point. Please do keep your microphone muted and your camera turned off. And I think the other point that I want to mention is that we don't want today to be the end of the discussion. We're very keen to keep conversations going. So although we can't see all your lovely faces on the line, please do let us know who you are when asking a question. So try to remember to add your name to the questions that you ask, so then we can follow up afterwards where necessary. So that's it from me for now, and I'm delighted to introduce Tony Green, Project Director for Hydrogen at National Grid Gas Transmission.
Lovely, thank you very much, Tom, and I'd also like to extend my welcome to you all. When we set this up, we somewhat expected a small, maybe 15 to 20 people for should we say, a nice little dinner. I think we've got more of a banquet. We've got 110 people registered, and when I looked just a moment ago, there was about 65 on the line already. So welcome to you all. Really good to see so many people interested in this topic. And we're going to spend a bit of time looking at blending and deblending of gas. And this is from a networks point of view, a concept that we've been researching, that we've been looking at. And what we wanted to do was share some of the research that we've done to date, look at some of the potential use cases that are out there, and really draw on the combined knowledge from you as stakeholders to see where we take this next. So in the session today, we're going to share some of the research that has been led by Costain on our behalf, and it's been funded through the NIA program, and all the distribution networks have provided funding into this. And we're going to look through the various use cases and then really draw out some of the challenging aspects of it. And like Tom said in his introduction, we really want your feedback here, because I think there's some real interesting opportunities here on how we can take this forward. So we're going to do a fair bit of Q&A during the session, so I'm not going to say anything more at this point, and I'm going to hand over to Lloyd. I'm handing over to Lloyd Mitchell now, Tom, or are we coming back to the agenda? Tom?
Let's go through the agenda to give people a taste of what's coming up.
Okay. So, as I said, we're going to have a look through some of the research project that we've led, hydrogen deblending, and Lloyd will lead that in a moment. We've then got Petrofac joining us to talk about offshore gas processing. So effectively gas separation and blending from the offshore world and how it's done there. And we'll have a bit of Q&A after that. And then, as I said, we're going to focus in on some of the use cases. And we've got representatives from the different networks and also from the power sector to talk to us in that area. We'll move it over to some Q&A. And then we will wrap up around some further opportunities and next steps, looking at some of the projects that are already underway and where deblending might play a role. So that's the outline that we've got for you. And at this point, I will hand over to Lloyd, who will now go into some of the research we've been doing on hydrogen deblending.
Thank you very much, Tony. So as I'm up first, I'll give a bit of the context around why we're interested in this as the networks, and then I'll give a bit more detail about the project that Tony alluded to that we did with Costain. So next slide, please. Oh, who's in control? Okay. All right. So why are we looking at deblending? Well, one of the challenges we have when thinking about moving to a hydrogen gas system is that we're at natural gas now, and transitioning to hydrogen is not going to be done overnight. We're not going to be able to snap our fingers and go from 100% natural gas to 100% hydrogen. So it's hard to imagine a world where blending doesn't have a role to play in allowing us to make that transition from where we are now to the gas system of the future. So that presents some challenges in that we've got to manage different gas qualities, different customers wanting different products, and so deblending has cropped up as a potential solution to some of those problems that we can utilize on the networks. So as it says there, certain customers will be unable to accept hydrogen blends. So one of the examples we use as the transmission system is power stations, because some of those power stations have turbines which are particularly sensitive to hydrogen. And so strategic deblending at particular locations can allow us to give certain consumers in an area hydrogen, certain consumers natural gas, and really help us manage that transition. So next slide, please. So it can be a hard thing for people to get their head around. What does that actually look like? So there's a very basic illustrative example here that I'll just go through very quickly. So I'm going to have to flick through the slides very quickly, sorry, but so start with the 100% natural gas system as it is today. We've got some distribution networks, power stations, industrial consumers, but now thinking about moving to gradual increases in hydrogen. Next slide, please. So if we start to introduce maybe 10% on the natural gas, we've seen evidence that distributions may be able to handle 10% without much of an issue, but maybe some industrial consumers, power stations will be a bit more sensitive, and so we'll have to have deblending facilities there ready to ensure that they have the gas quality they want, whilst the distribution network soak up that additional hydrogen that's on the network. So next slide, please. Oh, there we go. So yeah, if we look at maybe a distribution network converting to 100% hydrogen, so they're able to soak up a greater proportion, so have a deblending facility there to make sure that they get 100% hydrogen coming off at that offtake, and then the rest of the gas, the blended gas, carries on down the network to the rest of the consumers. So next slide, please. And as you step through, incrementally increase, maybe an industrial consumer switches to hydrogen. Next slide, please. And then you sort of get the picture. Gradually, we get more and more offtake switching to 100% hydrogen, and gradually, if we go through the next two slides, I believe, we make our way to 100% hydrogen. So that's a sort of very basic vision of how this could help us manage that transition and the framework for starting this project. So if you go on to the next one, please. So what do we look at the project? Well, this was, I believe this is the first NIA project looking at hydrogen, which collaborated between all of the networks, which is a really promising step. We're all on the same page when it comes to this technology. And it was partnered with Costain, who were the delivery unit for the project. And we also thought, because essentially all of us in the project have skin in the game, so to speak, we wanted an independent peer review done of the technology to make sure it did stand up. And so we've involved Imperial College London and the University of Edinburgh to review the reports. So it was a techno-economic review of deblending technologies and their application. So we went through the use cases on the network, the available technologies, the technical and economic evaluation, and then looked at what a potential demonstration project could look like. So next slide, please. So looking at the use cases, so it's all focused on offtakes for us because we don't use any of the gas for transport, or very little of it anyway. So we analysed a broad representation of offtakes. So we looked at all the NTS offtakes managed by National Grid, as well as the LTS offtakes managed by Cadent and NGN, and showed a number of parameters. So some of the most important parameters are shown in this graph on the top right. So we're looking at winter gas flow and outlet pressure. And so what we ideally want is a lower outlet pressure, because a differential between the inlet and outlet pressure is good for driving the process, and higher flows make the process more economical. And so looking at this distribution gave us a view of the use cases we would use to develop the study. So those are in the table in the bottom right. So representative 1 million cubic meters for an LTS installation with an inlet pressure of 30 bar and outlet pressures of 2 bar, 20 bar, and then a sensitivity at 30 bar. And similarly for NTS offtakes, 3 million cubic meters, inlet pressure of 60 bar and outlet pressure of 7 bar and 30. And those were used as the basis for the techno-economic evaluation that was done later on. So as I said, most important factors: inlet pressure, outlet pressure, and flow. And these are what we focused on, but there were a number of other parameters that were considered as part of the study. So next slide, please. So what are the technologies? So we considered a number of technologies as part of the process. That included, technologies that are widely used within the chemical industry with very high TRL levels. But we also considered some of the newer emerging technologies, such as palladium membranes, electrochemical separation as well. But ultimately, in terms of use on the network, it has to be an established technology to really operate at the scale and the economies of scale that we're looking at. So going forward in the study, we focused on a combination of membrane separation and pressure swing absorption, as well as cryogenic separation as the two main methods of hydrogen separation. So next slide, please. So looking at cryogenic separation in a little bit more detail. So this uses the gas pressure drop. So through the Joule-Thomson effect, it naturally decreases the pressure of the gas, and that drives the refrigeration process. And that's one of the reasons why deblending is particularly suited for the LTS and the NTS, because there is usually quite a significant pressure differential, which can really reduce the energy input required for these processes and drive down the costs. But the hydrogen, what happens is the hydrogen remains as a vapor, with most of the other gases within the stream dropping out as a liquid, as it's called. So what this leaves you with is a high pressure hydrogen stream, and that's pretty well suited to bulk separation, but it does require some pre-treatment to ensure that there aren't other gases within there that will stay in the vapor phase. So at the top right, we've got some representative costs. So the costs are quite dependent on the flow. So the greater throughput you have through your system, the more the costs drop, and also the greater concentration of hydrogen in your inlet gas. So it seems to be a bit difficult to see on these slides here, but what those two graphs at the bottom are showing are the hydrogen recovery costs on the left, so on the y-axis, and on the x-axis is the hydrogen concentration within the gas. And what that's showing is that as the hydrogen concentration increases, the cost of separating that hydrogen out decreases quite significantly, So you can see around 7.5%. I'm struggling to see here, 10% maybe. The cost, there's a bit of an inversion with cost where it becomes a lot more cost effective to separate the hydrogen out. So if you move on to the next slide. So this is similarly for membrane separation with combined with pressure swing absorption. So this is a two-stage process using polymer membranes for the bulk separation of the hydrogen, and then a well-known process in the industry called pressure swing absorption to remove the remaining impurities. The benefit of this is that it can achieve very high hydrogen purities, and it's very scalable, and there's little heating or cooling required. But similarly to the cryogenic separation, you see a similar profile in terms of the cost versus hydrogen concentration, again, where it's more cost effective at higher hydrogen concentrations, which could suggest that in the future these separation technologies might be quite expensive at first, but as we increase the amounts of hydrogen on the network, those costs will fall over time. So if we just go on to the final slide. Oh, there's one more. So this is just a bit of a quick view of what they're for. So the pressure swing absorption is really for that high purity separation, whereas cryogenic and membrane are for bulk separation, and they give varying pressures and concentrations. So for example, cryogenic gives hydrogen at high pressure, whereas membrane gives the natural gas as a high pressure. So it very much depends on the application, what you're looking for, which of these systems you will use. So on to the next final slide, please. So what are our next steps? So it was quite a promising view overall. The separation technology is definitely feasible on the network. It's going to be a question of looking at some specific cases and understanding the economics, whether those stack up. But the next view is to take a network-wide assessment of the UK gas transmission and distribution networks to understand where this technology might best be deployed. And then similarly, we need to demonstrate that it can be used at scale. And I believe Tony will be talking a little bit later about the Future Grid programme, which is looking to do that later in its later phases. Okay, thank you very much. That's all from me.
Thanks, Lloyd, and to Tony for setting the scene for us there. So we've already got some questions coming in on Slido, which we'll come to in a minute. Do keep those coming in. First, though, we're going to hear from Lorman Correa. Lorman is a process engineer and study manager with Petrofac. He focuses on engineering developments for the oil and gas processing and refining industries. He's worked with integrating and evaluating technologies for gas pretreatment, fractionation and cryogenic processes for LNG, as well as refinery flow sheet optimization, hydrogen and heat integration, engaging with process licenses and implementing open art technologies. And Lorman's here today to share with us his view from the offshore experience, so relevant for today's discussion. Lorman, over to you.
Hi, thanks very much for the introduction, and good morning, everyone. Yes, if you could please move to the next slide. Okay, just a little bit of background. Thanks for the introduction. I spent probably the first decade of my career doing refining processes, so a lot of the PSA, which is more associated with the onshore world, it's there, and quite a lot of the 10 to 15 years doing the gas processing onshore and offshore. Basically, why offshore? Why are we discussing offshore, and why is gas processing? The first part of it is understanding your feedstock. What are you using? What are you putting in the system? Understanding your feedstock will tell you whether you need to do a lot of pre-processing to get rid of the impurities, such as heavy hydrocarbons, others such as mercury, hydrogen sulfide, CO2, any moisture in your gas, any heavier hydrocarbons or BTEX processes. These things are relevant. Why? Because every processing, every processing technology that we go for, depending on the technology we go for, will require a different level of processing of impurities before it reaches the deblending stage. This is what we do onshore, and this is exactly what we do offshore. Of course, offshore, we have a much richer sort of stream where we have more of these components. Perhaps in the pipeline, these contaminants will be found in less proportion, less concentrations. But the process remains the same. And so whether you need to condition your feed to the deblending unit, or you need to do that preconditioning to achieve a desired specification to your final user, your process offshore, onshore, they are very, very similar. And the message from this is these are very solid industry processes which have been around for decades, literally. If we could move to the next slide, please. Exactly. So if you look at the graph on the top left-hand corner, it talks about complexity, and it talks about the onshore world, the offshore world, fixed platforms, offshore world, floating. So, and increasing levels of complexity as you get to the offshore floating. So the key message is, if we can do it offshore and in offshore floating, it's much less complex if we do it onshore. Of course, there's a message here as well that offshore, one of the complications, apart from sea motions and the marine environment, we have a reduced available plot space, which also presents a few challenges. But this is all well understood in the offshore industry, where modularization is key. We need to be able to build things compact and that can be lifted and transported and fit into position with as little effort as possible. And this has been done in huge FPSOs. I've had the honor of being involved with some of these designs in floating LNG facilities, and more recently we call it an FPSO, but it isn't really an FPSO. It's a huge boat processing a billion standard cubic feet per day of gas using these same gas processing technologies. And just to put it in context, about 30 million cubic meters per day. So the scale is there, the complexity is there, but they are all understood in the world and in this industry. So, and I would say that to make these projects more feasible in terms of implementation, we strongly recommend having an offshore approach to the onshore world. In terms of, we have a similar situation offshore that we have onshore in the UK. We have land and we have labor costs. So land comes at a premium, labor is at a premium. So we need to find ways of making things smaller, for a smallest plot space, and affordable, quicker to build, so we can mitigate some of the labor costs too. That's why I say offshore approach to the onshore world. And finally, this in terms of the Petrofac experience, we obviously, there's the gas processing side of things and the refining side of the world, which come together with this sort of implementation for gas deblending, particularly for hydrogen production, because hydrogen currently has no particular use in the offshore world, just because we haven't gotten there. And but it blends really well, and with what is happening downstream once the processing is performed. So that's it from me. I hope I stayed within the 5 minutes.
You did. Many thanks, Lorman. So we're now going to have our first Q&A. So let's head over to Slido and see what questions we have for Tony, Lloyd, and Lorman. So a couple in, and do keep those coming. So the first question from Julie Cox at Energy UK is, can technologies operate flexibly to meet gas demand profiles, or is local storage needed? So Tony, Lloyd, perhaps you've got some initial reflections on this from the research undertaken to date.
So Yeah, I can pick up on that first, if you like, Tony. So this study itself didn't go into storage. That's why one of the key next steps is looking at a sort of whole network context. But storage is always been quite a big part of the picture. So, for example, we did a study not long ago with SGN, Aberdeen Vision, looking at St. Fergus and looking at in blending hydrogen in only very small quantities into the NTS there. And even just to maintain a 2% blend, you probably need storage because the units used to blend the hydrogen can only turn down so much. So the big variations we have on our networks, the peak day could be 10 times the flow of the lowest flow day. So we're always considering that element of storage. I don't know if you want to add anything to that, Tony.
No, I think you've covered that. Thanks.
Okay, thanks.
Thanks, Lloyd. So another question is also about the research undertaken to date. Was consideration in that given to managing the gas composition at different locations on the network?
So similarly, it wasn't an explicit part of the study. That's looking at the wider network, but again, another very significant consideration. So we already have, we already closely monitor gas quality as it goes through the network at various stages. We would have to implement new systems to monitor specifically hydrogen blends, because it's unlikely that all our existing equipment will be able to measure that sort of gas quality. And so it's with that in mind that we'll be looking to include additional gas monitoring, because we've already got a complex gas system, but it's going to become more complex. So increased monitoring will definitely be part of the picture.
Right. Thanks, Lloyd. A question for Lorman on the cost reductions that have been seen in the offshore sector, particularly those that might have been achieved through modularization or repeat construction.
Yes. Okay. It's an interesting question. Of course, in terms of repeat engineering, repeat construction, it all depends on the economies of scale and how we can place those contracts for manufacturing and manage them on a cost reduction point of view. I mean, the discounts on workloads, on work fronts. The modularization point in the offshore world is a bit of a tricky one, because many of the things we build offshore, FPSOs or platforms, are modularized anyway. I would say for onshore, where you have remote locations, you have to stay within a boundary of transportation limitations, and you want to speed up construction in place because it costs you fundamentally a lot of money. Then the benefits are very much linked to what that labor costs is in the place you're building the facility. So in the UK, I'm guessing, just out of my, it would range probably 35–40% of your cost would probably be associated with the construction. And as much as you can do to reduce those construction costs, because you shorten the time of implementation, the better off the project will be.
Thanks, Lorman.
Does that answer the question?
It does, yeah. And another question that's come in also relating to costs, which perhaps picks up the slides that you presented, Lloyd, in terms of how the costs vary with hydrogen concentrations, and specifically whether the costs that were shown on the graph were for deblending per kilogram of hydrogen.
That's so interesting. I suppose that links up with the previous presentation, and and it will depend on the level of processing you require. So you will have to be a combination. Unfortunately, it's not a response that is completely direct. So you need to assess first the level of preconditioning or treating you need to do to that particular stream, and then assess the hydrogen purity you want to achieve, and that will determine what process you need to follow, and hence that will determine your cost base. No doubt, the higher the concentration in the network, the easier it is to separate all hydrogen to a certain extent.
Yeah, and to pick up on the question about the graph in particular, it was showing specific costs. So yeah, that cost per kilo of hydrogen. So yeah, you would expect it to decrease, but it is dependent on so many different factors: the differential pressure, the flows, the hydrogen concentration, what purity you need. So we use these representative use cases for the study, but really any kind of use of hydrogen deblending is going to have to a very specific bespoke study looking at those operational parameters that you need at that location.
Great, thank you both. So another question that's come in is about the size of the deblending facilities, the sort of the space that those would take up and the extent to which those would be appropriate across the GB network. Has there been any consideration of that to date?
So the study did do, it wasn't a main deliverable, but we did look at the footprint of a representative facility, and at the moment they are quite large. It depends, because some of our offtakes, particularly to large consumers, are a reasonable size of a ground installation anyway, and you might feasibly be able to get it within the footprint of the site. But it's likely that with the scale of the technology, for many sites, it wouldn't fit within the existing footprint. But that was kind of one of the interesting things on the agenda for this study is looking at the learnings from the offshore industry. Maybe we can take those onto the onshore and have that sort of compactness and manage to fit the kit within the existing footprint. I think that would make it a lot easier, because extending sites can be a significant additional cost.
Thanks. And the other question that's come in is on how we are ensuring that work is coordinated across the networks. Lloyd's already mentioned the work done with SGN on Aberdeen Vision, and later on today we're going to be hearing from some of the other networks on related projects. So I think we'll pick that up later on. So many thanks for your questions then. As I said, do keep them coming in, or do keep rating other people's questions. So we're now going to have a series of short presentations on use cases to hear about how hydrogen deblending could impact the domestic setting, how it could be used in transport, in industry and in the power sector, and what the experience would be and what the opportunities could be. And then after those 4 presentations, we'll have a further Q&A at the end. So as I say, do keep your questions coming in as you think of them. So Adam Badley from Progressive Energy will discuss deblending in industry. We'll hear from David Jones from Cadent on transport use cases, and then from Phil Cahill at RWE on the perspective from the power sector. First, though, Keith Owen will present on the domestic use case for deblending. Keith, over to you.
Thanks, Tom. Good morning, everyone. So quickly then, Tom, if you could move me to the next slide, please. Thank you. So within industry, there's been work going on for some time now to understand the challenges of conveying hydrogen through our existing gas infrastructure. That started out, as say, a few years ago now, and from an oil and gas networks perspective, as the lead for H21, we're really pleased that this is very much a collaborative industry project to understand all of the technical challenges, the issues around society and so forth, so that we can answer all of the necessary questions which would be required in order that government have the confidence to make the sort of policy decisions that would underpin a move to a hydrogen gas system. So very quickly, the H21 project is just about to close out phase 1 actually, and we anticipate the reports to be published around about August, September time. There's been a number of parts to that. One over at the HSE research laboratories in Buxton, looking at the comparative differences our existing assets exhibit conveying natural gas and then switching to hydrogen, to understand how that behaviour changes, what the leakage process might look like, and so on. We've also been looking at the consequence of that leakage over at the Spade Adam facility, operated by DNV-GL in Cumbria, so that we really get a solid understanding of how different hydrogen will behave and move around in soil structures and so forth if we were to move to a hydrogen-based heat system for the UK. Wrapped around all of that is the development of quantitative risk assessment for hydrogen. Now, this is something that exists already for the natural gas industry. It's an essential component of everything that we do in many respects, in that it understands the various risks and probability and wraps all of that together. So we've got a very comprehensive understanding of lots of different scenarios and just how natural gas would behave. And we need precisely the same thing when it comes to conveying hydrogen. And all of that then infers back into the new standards, the new processes and the procedures that we undertake in order to manage a safe, reliable and effective gas infrastructure for the country. If you move to the next slide, please. Thank you. As I mentioned, it isn't just about the technical. I think it's essential that we really understand how this will impact customers that are currently using natural gas, or indeed not, to get their views and their concerns recognised, understood, and to communicate in a way which is easy for them to understand, because this is quite a technical area that we're talking about. It's a momentous change to move to hydrogen, but certainly an essential one if we're to deliver rapid decarbonisation of heat and hit that net zero target for the UK by no later than 2050. So really important that we run social sciences, really important that we have that conversation, and we've already had some really positive feedback from members of the public expressing concerns, understanding what we're trying to do. What's really I think promising is that customers really want to engage with this. They're really interested, and they want to understand what we're trying to do. And I think that's important if they're ever to make the right choices for them in whatever heat solution they might wish to adopt for their individual circumstance. So it's a little bit about social sciences. And then just to close out, if you move to the next slide, please. So I've talked about what we've been doing in phase one, but that's not the end by any means. Phase one's been all about individual asset. We're now moving to phase two, and that's starting to look at the conveyance of hydrogen from a network perspective. What are the different challenges that we would see once we have all of these bits of asset connected together? So in that context, we are developing a microgrid over at the Spade Adam site, and that will allow us to understand all of our network operations, how we manage a hydrogen gas pipeline system compared to that of natural gas, what differences, what new techniques might we need in order to manage that in an appropriate manner. As part of this, we're also undertaking unoccupied trials. What we tested so far is asset that we harvested from around the UK as part of the mains replacement program. So by doing that, we're testing the assets in an unnatural situation, i.e. they're above ground all of a sudden, they've been soil structures being removed from them and so on. So it's important that we validate all of our findings in an unoccupied trial, a part of a network that's never been disturbed. So we see that all of those results stack up, stand up to that level of scrutiny. There's some work to combine the QRA work that's been done so far with the work that's been carried out in the High for Heat programme. which would then provide a Q area that's not just looking at the pipeline network, but all the way through to the burner. So again, an important next step. And then we could, continuing with that social sciences work, to really get a firm handle on where we need to take that. And then just as a final piece, once we finished all of that in phase 2, and we're just getting underway with that, we're already thinking about, well, what happens with phase 3 and moving from the unoccupied trial space into fully occupied trials, the sort of thing that we're seeing with High Deploy 2, which is a blended gas program where we're working with 670 existing natural gas customers up in Gateshead. I think it's really important that we take that next step to work directly with customers and understand precisely how to do this, how to keep customers happy, how to keep everyone safe, and how to deliver a really low-cost hydrogen gas network for the future. So that's a little bit about domestic. I'll hand back to Tom. Thank you.
Many thanks, Keith. And I'm going to straight away pass to Adam.
Great. Thanks, Keith. Thanks, Tom. Morning, all. Thanks for turning up. Yeah, I've probably not time to say too much about Progressive, but suffice to say, we're leading the development of the HyNet project, which hopefully you're familiar with. And HyNet has a major sort of blending element, so we're obviously interested in this work. Just this slide should give you just an idea of the sort of geography of the industry sites around the sort of what we call the Northwest Industrial Cluster, which links into HyNet. Many of those sites we've been working with since project origination for HyNet, so about 4 years. This slide doesn't show the hydrogen, it's got the CCS or the CO2 pipeline on it going out to Liverpool Bay. Doesn't show the hydrogen pipeline, but it's worth saying that we've just completed pre-feed on that pipeline, and we're not far off from kicking off feed for phase 1 of the pipeline that will connect some of those industry sites. Next slide, please. Apologies for the wordiness of this one. Really, it's just to sort of some early thoughts and really to sort of raise some questions. I don't necessarily have the answers for these, but in respect of whether deblending could be useful for industry, I think the first key question, first sort of, I guess, opportunity, I guess, which was mentioned by National Grid earlier, was access to hydrogen for use as a fuel for industry, which could facilitate earlier conversion of plant located outside of industry clusters. I think those located within industry clusters will largely get a supply with a dedicated hydrogen pipeline. I think this was a point raised earlier again, and also in a question, but I guess the challenge associated with that, with deblending of hydrogen, would be the sort of, if you're doing that at large volumes, the impact that would have on the blend, the percentage blend supplied to others. That could cause, certainly for industry issues with the burner, which may if you've got variable amounts of hydrogen coming at any given time, that could present a lot of challenges. And of course, with metering, as I think someone alluded to earlier, I think that those are the sort of key challenges, but possibly a good opportunity. I think the other one is removal of hydrogen to enable ongoing use of natural gas by industry, at least in the short term. Certainly on HyNet, we want to blend into the distribution network. There are some challenges associated with some forms of industry or types of heat and power generation in industry that can't be as easily converted to hydrogen, or the evidence isn't there yet. So deblending to allow natural gas to go to those plants could be a useful thing to do. Particularly relevant, I'll talk about a bit, for forms of direct firing, like ceramics and glass sector, but also for CHP. So that's an opportunity, but alongside that, question is it simpler to develop the evidence base as we're doing actually at the moment, to enable those sites to operate on hydrogen rather than go through the complexities of deblending. So there's a bit of a question and balance to be had there. Next slide, please. So this is the what we call the HyNet IFS, the HyNet Industrial Fuel Switching Program. It's work that's been sponsored by BEI's Industrial Fuel Switching Competition. So this is a program of work that we are smack bang in the middle of. Just briefly, I mean, we are, as Progressive, leading this work. We have 6 work packages. We're being supplied with hydrogen for the project by BOC as a contractor. I think possibly the greatest challenge associated with this program of work is getting sufficient hydrogen, which has meant that we've had to scale back some of the scale of demonstrations. We have a direct firing package at Pilkington Glass, where we're actually going to be putting hydrogen into a blend of hydrogen into a blend and going up to 100% hydrogen into parts of the glass furnace at St Helens. We have the boilers work package, where we're doing, I guess, a pre-trial at Dunphy Combustion in Rochdale, ahead of putting up to 100% hydrogen into Unilever's Port Sunlight site. And I should emphasise both Pilkington and Unilever, those are going to be live trials. It's going to be in a fully commercial environment, commercial scale. And then work package 6, we're undertaking a FEED study for a new hydrogen CHP, a new gas turbine at SR Stanlow Refinery. It's not a demonstration in that one, largely because in contrast to boilers at Unilever and the glass furnace at Pilkington, the existing gas CHP is not really able to take high proportions of hydrogen. I think with CHP, we're largely looking at replacement turbines, so new kit rather than conversion, which is the case at a lot of other sites. Next slide, please. I hope I'm okay for time. This is actually my last slide. So the objectives of the programme are to provide evidence. We want, obviously, our participating sites to be able to convert hydrogen as soon as we can supply it from the HyNet project. We want that evidence to be transferable to wider sites, not only within the Northwest, but also beyond. We can convert as many sites to hydrogen as possible as soon as it's available, particularly in the different clusters across the UK. We want to determine the costs of converting to hydrogen. And as I said, it's mostly conversion rather than buying new plants and equipment. I think it's surprising, actually, how little the capital cost of actually converting some of these sites is. It's obviously the differential between the cost of natural gas and hydrogen, which is the challenge that we need to bridge via forms of support and long-term policy mechanisms from government. We want to prove, obviously, there's no detrimental impacts upon existing plant and equipment. And we also want to demonstrate that hydrogen can be used safely, which is obviously a critical consideration, and can meet all of not only safety regulations, but also that there's no greater environmental impact than current use of natural gas. So no need for significant permit variations, particularly as you'd expect with regard to things like NOx. So that's all I've got to say. I can't check my clock. Hopefully I'm broadly within 5 minutes, but thank you for listening.
Many thanks, Adam. And indeed for keeping to time. I'm going to pass straight over to David.
Thanks, Tom. So thank you for giving me the opportunity just to introduce transport and to discuss the potential of hydrogen as a use case. Next slide, please. I just wanted to set the scene and just provide a little bit of background. I think with net zero, the transport landscape certainly changed, and we see a much greater role for biomethane and hydrogen in the evolving market. I think it's fair to say hydrogen has the potential to meet a significant proportion of future mobility demand. And if you look at the scenarios generated by a number of actors, you see a range of emerging between 25 and 140 terawatts, which is pretty significant. And a central case would give you around about 80 terawatts, which seems reasonable. So that's a sort of starting point in terms of the scale. But I think it's fair to say that, you know, plans to scale and achieve that that level of hydrogen production and delivery face significant challenges, and that's what we're looking at today. But I think overall the majority can be overcome. Next slide, please. So we've heard quite a few discussions today about the importance of economics and prices, and I think that's true. We've got to bear in mind what the users expect and what they are prepared to pay. Decarbonisation is absolutely necessary, and I think, you know, hydrogen has a clear role to play in the mobility sector. It's very useful. It provides great advantages in terms of some of the key hard to decarbonise sectors, and this graph illustrates almost a creaming curve between the different options, starting with the harder to decarbonise type applications to the left, and then moving to the right, you see lighter commercial vans and cars. But the important takeaway is there's a range of prices here between $4 and $6 a ton of, dollars per kilo of hydrogen. And that's important because that's sort of matching to the potential energy demand, and that would see you achieving something in the range of between 15% at the higher level of $6, and potentially around about 50% if you are able to get it around about $4 per kilo. So an important metric. And from that, you also identify some key segments like trucks, long distance buses, larger passenger cars, rail is another potential. So the opportunities, if we can achieve those prices, is that hydrogen can be extremely competitive. Next slide, please. And this is some work we carried out with support from Adam, actually, from Progressive. This was looking at a transport layer over the HyNet projects. So this is really for new hydrogen, new pipelines, new refueling infrastructure. And the graphic on the right provides an overview and comparison of the different costs between the more expensive use of on-site electrolysis. Off-site electrolysis is placed in the middle, and then we see HyNet, which is grid-supplied hydrogen from the project using new pipes and new infrastructure. We see that providing a very competitive price. So overall, that provides something in the order of 40 to 70% lower cost than the alternatives at 2019 prices. So that provides us with a good opportunity to position the use of hydrogen networks and new networks specifically in the transport sector. I think it's fair to say hydrogen cars, buses, trains, submarine are reasonably well developed, but what we're missing is policy and infrastructure, which is what we're discussing today in terms of making this happen. Still challenges with getting some of these segments opened up. I'm doing quite a lot of work with HGVs at the moment in the UK. And what's interesting, although it's not developed yet, it's probably one of the most important sectors because of its scale. And an important point that we need to consider is the cost of managing impurities and contaminants, especially if we're looking at older networks. What we think is that the use of hydrogen in new infrastructure will provide a sensible, a reasonable, competitive price, as indicated in the graphic, at about £3.60, and that's in sterling per kilo. Next slide, please. So the previous slide was all about the new and the HyNet project and what we know quite a lot about. But what if we want to actually inject and blend into existing networks? Well, we commissioned an NIA project called Hydrogen Grid to Vehicle, and this essentially looked at a variety of permutations of hydrogen production sources, whether it was 100% or blends with natural gas. This illustration is providing an overview of a blended system, which is what we're discussing today. The results and what we found was that, generally speaking, hydrogen production is pretty clean and the output is compliant with transport fuel cell standards. However, if we look at the sources of natural gas before blending, typically there are contaminants that would cause problems for fuel cells. So by mixing the two, clearly we're looking at a potential issue. If we then go on to deblend and supply to heat, as we heard earlier, I think the heat standards for HyNet, the quality specification can be achieved. So I think we're okay for heat. But certainly if we look at fuel cells and their use in transport and the quality requirements for fuel cell vehicles, we see a challenge and the need for purification. And those challenges manifest themselves in terms of the presence of odorant. So we've got to manage sulfur or sulfur contaminants. We also need to consider the hydrogen quality obtained after deblending. What applications, as I say, for transport, we're going to need to think about that quite carefully. Purification steps are certainly required after deblending. And a lot of that comes back to contamination of the hydrogen from the gas itself, and also if we're using repurposed networks, particulate material and residues in the network. I think purification for transport is feasible, technical. Technologies exist, but I think we need to probably move further. And we certainly need to understand contaminant and concentration variation across the network before we can apply specifications or develop specifications for specific technologies. And that variation is an important consideration. And to summarize, I think the new PE network provides less contaminants, and therefore the focus moving forwards is certainly we need to think a little bit harder about the use of repurposed networks. Next slide, please. So drawing that together and coming up with some key questions, I think overall there's no strategic plan currently in the UK to scale up hydrogen in transport, so it's early days. But the DfT are working on their decarbonisation transport plan, and we're actively supporting that. And I'm really keen that we develop a proposition for networks. I think that, as we've seen, has got a great opportunity to provide cost-effective hydrogen for transport applications. However, we need to consider hydrogen delivery by the network, and specifically the need for cleanup due to the nature of contaminants that we've identified in the network itself. Whether that comes from blended networks or 100% networks, certainly using repurposed infrastructure, I think we need to be mindful of what needs to be done to clean up that fuel prior to putting it into fuel cells. That leads on to gas quality standards. I think we see those reflected in heating specifications and use of hydrogen for heat, less so for hydrogen for transport, and there's a whole debate about that in the future. I'm really keen that we never lose focus on what customers are prepared to pay, and I think overall the work that we've done would suggest that future hydrogen prices at pump need to be competitive, and that's sort of putting it in a range between 3 and 5 kilos. And that's probably out to 2030. That's the sort of time horizon where we see those prices taking effect. HyNet has shown that we can achieve that with new infrastructure, but there's questions over use of existing infrastructure. And we need to also be mindful of the need to make sure that we have an investable transition pathway as we move from what we do today to the future. And that's specifically between biomethane and hydrogen to support transport. And we're leading some work on that. To identify that pathway and provide a narrative. And finally, I think there's certainly a need for early demonstration to address the challenges that I've identified here, and to develop experience and provide confidence to those who are going to make the decisions, policy, technology selection and development, etc. So hopefully that's answered the questions and provided some insights into transport and how deblending and use of hydrogen can impact the transport market. I'll hand back to Tom.
Many thanks, David. Much appreciated. And I'm going to hand straight to Phil Cahill.
Okay, if you can just move to the next slide, please. Okay, so I was asked just to say a few words about deblending and from the power sector. I think number one is we see existing CCGTs being part of that initial demand for hydrogen. So I think the hydrogen's coming our way, and obviously Tony in his introduction talked about the power stations in particular as being sensitive users, potential sensitive users. My overriding point is I think we'd like not to be a sensitive user. We'd like to be part of that demand. I joined in the South Wales Industrial Cluster meeting earlier this week with the Energy Minister, and he definitely does see the existing infrastructure being converted in the way that the first speaker suggested to gradually move into 100% hydrogen. I think it was clear there isn't going to be a separate hydrogen grid. So I'm not trying to do a selling point on RWE, I'm just trying to sell the context here. We're committed to being carbon neutral by 2040. We've now got a large renewables business that's come in. Hydrogen's really important to us, not just for use, but potentially from renewables. We're colourblind towards hydrogen, so no discussion about where it comes from, other than cost, obviously. We've got 6 major CCGTs, so I think we're probably the biggest customer on the NTS with that 7 gigawatts. So we are a really interested partner, shall we say, for this transition to hydrogen. We've got a range of plants. Our plant is mainly GE and Siemens, including some of the newest and most efficient plants, i.e. they're not great for being test rigs. And the size of them means that also it's really difficult to, so Adam Baddesley said all the points he made about hydrogen for industry, they translate directly into the power station business, but it's a different scale. And just getting the hydrogen to prove the equipment and prove some of the things that we need to prove is going to be a challenge in itself. So just moving on to the next slide then. I'll try and pick up on this slide some of the challenges. So for instance, our most efficient CCGT down at Pembroke there, it uses more than 50 tons an hour per unit of natural gas. So we're using more than 250 tons an hour. So I did ask the question about the cost of deblending, because the costs that I think I saw going from 60 bar to 30 bar using cryogenics were around about 1.3 pounds per kilogram. Sorry, right about £1 a kilogram. So we're looking at adding £50 a megawatt hour just for the deblending cost. So again, key takeaway: if we don't need deblending, that is a really good thing. It's with the scale of what needs to happen for the power station is clearly huge. And so are we sensitive users? We've got a lot of views from the OEMs that suggest maybe 15-20% can be tolerated into the plants. We've got some technology in the newest plants with sequential combustion, which is probably more suited towards a higher level of hydrogen. And so I guess we may be sensitive users at a certain level of concentration of hydrogen into the system. And we don't want to be obstacles to hydrogen blending into the system. The challenge is clearly the commercial implications, not just for the cost of fuel, but then the cost of deblending has to be borne by somebody. You know, there's a lot of work at Bayes on the business models that has to work. Then there's technical issues and contractual issues, quite frankly, as we get into the discussions with the OEMs. There's one thing indicating that we can burn a certain level of hydrogen. There's quite another making sure that we're not carrying all the risks, the commercial risks around that. And there's issues on the variability and the rate of change. I think there was a question earlier about control of deblending systems. Pembroke, for instance, has got a gas quality monitor on there, so we can adapt the firing system. What do we need to do in terms of hydrogen concentration? And then, as I say, there's we're into the operations and maintenance of the plant. Do we need to have different settings on the control system as we move into different levels of hydrogen? What are the maintenance implications, not just in terms of the intervals, but the contracts we have, the commercial contracts we have with the OEMs. And then the final point is, how do we establish that we can take that level of hydrogen given the scale of what we do? And I think in a discussion with Siemens to run one of the combustors for one of their GTs, they had to virtually take all the available transportable hydrogen in mainland Europe to run it for a fraction of a day. So, how do we get that level of confidence? So we are doing things. We're doing things as part of the South Wales Industrial Cluster. We're sponsoring an engineering doctorate down at Cardiff. So we're an informed user. So we need to inch our way towards it, and we need to do appropriate testing. And with a power station, I think the only place we're going to get to testing to understand the need for deblending is actually using a sort of live power station and firing up a section of the grid with hydrogen. Okay, hope that prompts a few questions and thoughts. That's just a quick perspective from the power sector. Okay, thank you.
That's great. Thanks, Phil, and thanks to all our presenters. Really interesting to hear the different perspectives, considerations, and the issues of focus for those different use cases. Now, I think, unfortunately, Adam's had to leave us, but our other speakers are on hand to answer your questions.
for 5 minutes, actually. Tom.
Well, I'm going to come to you with the first question then, because there was one directed to you.
Yeah.
So it was whether you'd come across any showstoppers for deblending.
I guess we haven't been looking at deblending as such with our project. We've been looking at blending, and whether we can industrial sites can take a blend. I think it does depend. It obviously depends on the type of heat and power generation, whether it's a boiler or a furnace or whatever in place. I don't think we are, certainly, boilers are fairly ubiquitous across the network, industrial boilers. I don't think we're expecting any issues with putting up to a 20% blend into the majority of boilers. I think that's likely also to be the case with the glass furnace Pilkingtons that we're running the demonstration at. But no, apologies, I can't really answer. I can't really answer the question specifically around deblending. Maybe it's better for someone else to take that.
Okay, we might come back to that. With your point sort of related to one of the other questions that we got in terms of what levels of blending could safely go into the distribution networks without having to change boilers. So on this, the reason why Adam mentioned the 20% level, which is being tested through the High Deploy project, and as Adam mentioned, would be taken through to HyNet. That follows the EU's Gas Appliance Directive, which requires domestic appliances to be tested at that 20% level. But a follow-on question was on how much hydrogen production would be required to meet this 20% hydrogen content. So I wondered if anyone wanted to come in and address that point and whether that's been considered.
It's certainly, so it's Adam here. It's certainly been considered for the HyNet project. I did have some figures in front of me a few minutes ago because I was working on another report. But I think it's been considered for the HyNet, what we call the HyNet area. Broadly encompasses the area around that I showed on the chart, that the sort of with the industrial sites on earlier on. I think to put a network blend into that sort of full area, we are looking at about 3 to 4 terawatt hours of hydrogen per annum.
That's great. Thanks, Adam.
I can maybe.
Tom, here, if I can just add to that, if you look at that at a UK level, we on a winter's day probably put about 365 million cube of gas into the network. So if you take 20% of that as hydrogen, which has a third of the calorific value, and you equal that out, you're probably looking at over 200 million cubic meters of hydrogen needed. That's for the whole of the UK. So we're talking pretty large amounts of hydrogen needed if you wanted to do a 20% blend.
Great, thanks both. And just following on to address some of the other questions that we've had in terms of the rollout plan for hydrogen. So there were some specific questions about whether the networks are proposing a blend or proposing 100%, and whether the rollout would cover whole network areas or just pockets of the network. So a question perhaps that I'm sure that those from the networks would be happy to step in and give their thoughts on.
Hi Tom, it's Keith. It's a good question, and it's an area for discussion right now. When we look at what we're trying to achieve, which is to, at the moment at least, there's a strong focus on that evidence base to underpin a safety case for hydrogen. I think, and that's rightly so where we need to be right now. But we are starting to look at how might each of the distribution networks and the transmission system collaborate, work together to evolve our systems from where they are now to that net zero. And all options are on the table. So there'll be parts of networks where certainly in the early days that the blended solutions are really sensible transitional step to take. And they may well sit on that for quite some time in order to at least have some decarbonisation happening, perhaps with biomethane in the mix as well. For other parts of the network, because of the way that certainly distribution networks are configured, if you start to change part of your network to 100%, it leverages quite deep penetration of that quite easily if you choose to do it just through the construct of the network that we have. So potentially there is an opportunity to target the larger emitting areas in the first instance, the big towns and cities across UK, in order to make great strides in terms of carbon reduction, and slowly leverage out from that. So you begin to develop almost a hub mentality across UK where small hydrogen centres are established, and then you start to evolve out from that. That's one way of doing it. It's not to say that everywhere is going to be converted to hydrogen, much as we might quite like that. It is about finding the right least cost solution for different locations. So, if you're down, in some parts of the UK where electricity solution might be a more optimum way of doing things, then absolutely do that. That's sensible. But we do see a very significant role for hydrogen in the gas infrastructure, with every opportunity in many respects to penetrate all of the areas that it has right now. So it's a real mixed bag, and it's a bit of a messy answer, but it's just that's the state of thinking at the moment. Great ambition, real great opportunity there. Very large amounts of hydrogen required, as Tony alluded to, even at 20% levels. So there are a few things to join up here. It's fair to say, though, that irrespective of the heat solution, we're going to need really big amounts of energy production. So if you're going down the electricity route, it's going to have to be massive. If you're going down the hydrogen route, it's going to have to be big. So those issues exist everywhere, and it's just finding the optimum route through all of this in a whole systems manner to deliver the best outcomes for customers.
Thanks, Keith. And I'm actually going to go to a comment from Morris on the Teams chat, which is perhaps something for Tony and Lloyd to think about in relation to the opportunities that deblending would bring to this. So Morris has asked whether hydrogen would be needed to be injected at strategic points to enable the gas distribution network to have today to continue to be used, and whether the hydrogen would need to be produced on site at point of use, or whether it could be produced elsewhere and moved through the network.
I guess the answer to that is both are correct. It could be an either or. If you look at the maturity of hydrogen production today, if you want volume, you've really got to be looking at blue hydrogen. So SMR, reformed methane and carbon capture. If you're looking at small scale, green hydrogen is obviously the way forward at this point, but we clearly haven't got the scale. If you wind the clock forward 10, 20, 30 years time, I suspect we will see that green hydrogen has matured. The cost of green hydrogen will drop significantly, and we could probably be looking at a far more distributed hydrogen generation scenario. So I think both answers are valid. It's just a matter of timing. So in my view, I think it will be blue first. In the Gas Goes Green documentation, we've used the term blue is the gateway to green from a hydrogen point of view. Great,
thanks, Tony. So I want to dive into some of the more detailed questions that link into some of the use cases we heard about. So a question for Phil on whether, from your understanding, whether a power station could cope with fluctuating hydrogen concentrations, or whether the levels would have to be static and keeping within certain parameters.
Right. Okay. Well, I'll try not to give a woolly answer because the overall answer is depends. So it depends on the step change or whether it's a damped change in concentration. It depends on the size of the step change. It depends on the control system that's there on the power station, and it depends on the firing system. So, you know, we run through with our existing stations changes in gas quality, for instance, with heavy hydrocarbons. And so, you know, a small concentration, I would expect the plant to run change. I would expect it to run through. But there'll be certain points as we step through the control system where we've remapped the firing conditions, and then we'll either need a trigger to do that, either by some sort of monitoring or a warning, if you like, that gas quality is changing. So there isn't a simple answer to that one. Generally, we don't like sudden changes in quality or nature of the gas coming into the power plant. Does that sort of answer the question?
It does, yes, thank you.
There's a whole lot of work that needs to be done to do that, by the way, and there's a whole lot of expensive work that would need to be done with the OEMs to carry out the tests that would be needed to establish those the control parameters. And it's likely to be on each of the different stations. There are different Siemens machines, different GE machines, Mitsubishi machines, etc. And all of those will have subtle sensitivities to the rate of change and the absolute amount of hydrogen that can be tolerated without major replant, shall we say.
Yeah, no, thanks. I think that's an important point to note, that there's further work required across this piece, this thinking. So another question, this one for David, I think. So we had a couple questions on purity and whether piped hydrogen would be clean enough for use in transport. David, you touched on this, but I wonder if you can elaborate a little on what the H2GV work has shown in terms of contaminants or the impact of sulfur-based odorants.
So it certainly is an important point, and for me it is one of the biggest challenges we have when we start looking at end uses. And it's interesting to sort of hear the power sector in terms of their requirements, and I think, you know, you've got the industrial requirements, and transport's just another end use. But if you're using fuel cells, you're operating at a very high specification. You could argue it might even be too high. It's set by the OEMs. But in terms of the work we did around a hydrogen grid to vehicle, and I'll describe the new network tests, essentially, when we did contacting with PE pipes and looked at measurements from the network. We actually saw a relatively clean result. The contaminants present that would probably cause concern would be CO2 and oxygen and CO, and potentially some particulates or carryover if the new network's connected to an old network. So new networks and new hydrogen and relatively pure hydrogen, I think we can find solutions for. If we move to repurposed network, and the source of hydrogen, it can be from a production unit or it can be from deblending. But once it's into a repurposed network, the sorts of things that we measured and we identified, and the work was completed by MPL and partners. Certainly, we identified non-methane hydrocarbons, including aromatics, which would potentially cause concern. There's the methane, the nitrogen, sulfur compounds, obviously the odorant, and H2S additional compounds in the particulates. And we found all sorts of particulate material in the network that, if you contact with pure hydrogen, creates a problem. And others were formaldehyde, formic acid, and ammonia, or trace elements of those. And those all represent challenges when you start looking at fuel cell applications. So in my world, you know, I'm looking at some magical kind of technology black box that will take what, you know, heat is currently able to live with, and you know, convert that hydrogen into a purity that fuel cells can operate off of. And like I say, the driver is it's by far the cheapest way of distributing bulk hydrogen to these key applications, which include transport and refueling infrastructure. Hopefully that answers the question.
Great. Yes, thanks for those further insights, David. So one other question that's come in, that's perhaps for Tony or Lloyd, is thinking about the deblending process itself. How much CO2 is created through that process? So for the power required for that equipment, the power per kilogram of hydrogen that's deblended.
So I mean, it depends a bit on the process that's used. So that was one of the benefits to looking to utilise the inherent pressure differential in the network to drive the process. In that the energy, most of the energy for the process is already there in the form of compressed gas, and you can utilise that energy to drive the separation. So so in particular, cryogenic wouldn't require a huge amount of energy. Membrane separation, it depends on what you want your product pressure to be. So I said earlier, cryogenic gives hydrogen at a high pressure, and membrane separation gives hydrogen at a low pressure, and vice versa for the natural gas streams that are coming out. If you want your product at a higher pressure and it's coming out of the process at a lower pressure, then you would require recompression, and that's what's going to be the main energy requirement of the process. But if you can avoid that, there's actually quite a small energy input, and obviously depending on the source of your energy, that could be low carbon anyway. So in terms of the overall process, there's not a huge amount of energy input at the off takes to the networks.
Thanks, Lloyd, and that's positive to hear in terms of achieving net zero, of course. So I'm never one to try and close off discussion, but just conscious of time, I'm going to ask one more question to each of the panelists, and it's going to be the same question. And Keith, fair warning, I'm going to ask you first. So what kind of policy changes would be needed to happen to enable hydrogen in the networks and their connected customers?
Okay, start with a nice simple question then, Tom. Thanks for that. I think there are a number of areas that would be helpful in order to move us towards this newly decarbonised world. It's clear from some of the activity so far from appliance manufacturers that the deliverability of a hydrogen-ready appliance is really key. So a simple, and in many respects, a low regrets policy decision may be to mandate, as has been done for condensing boilers, mandate hydrogen-ready appliances, no later than perhaps 2025, because that sort of direction really gives confidence to supply chain, which I think is the one thing that is perhaps lacking at the moment, that confidence to invest in R&D, the production plant and so forth, and realise the potential for these new products, and also to drive the cost down, which is also very much key. So I think that's very important. I think it is incumbent on the networks and other industrial partners to be able to deliver the required evidence that would underpin a safety case back to our regulator, back to BEIS, so that these policy decisions to say we can see a route for hydrogen in the gas network, and therefore we'll start to bring forward that policy direction. I think it's those sorts of things that need to be sorted out first. There are quite a number of different areas that would enable and help and deliver step changes, and there's perhaps a way forward here which allows us to make smaller steps to keep progress going, not to unduly impact progress in the UK. And I think there's also a need, just to step aside from that policy ask, there is a need to work closely with what's happening in Europe, because we're seeing some pretty big noises coming out of Europe about hydrogen in the gas infrastructure, particularly in Germany. So I think making sure that at a high level, governments are aligned, because gas infrastructure is a bit immune to geography and politics. It just stretches everywhere, as does the electricity grid. So it's important that we have a really joined up view, but all of that needs to be underpinned by hard work and evidence from industry in order to establish that policy in the first instance. So I think that it would be wrong to say it's over to X to sort the problem out. This is a real collective effort to get this over the line.
That's great. Thanks, Keith. David, what would you say? It doesn't necessarily have to be transport focused.
So what would I say? I think around policy, three things. I think first of all, what we're looking at is an integrated hydrogen strategy in the UK. What I see is, obviously I look at transport, but I'm also interested in all the other end uses and applications we've discussed today. And I think we need something that brings it all together. And also some of the speakers have referred to systems, energy systems solutions. And I think that's another key part of it. So that would be my first ask. I think the second is around the transport piece. We need to be mindful that we need vehicles, we need infrastructure, and therefore there needs to be policy support and incentives to encourage that particular industry, that particular segment, and ideally, a mechanism that doesn't disadvantage consumers. So it really is about focusing on the delta that exists between what we have today or the counterfactual over time and the hydrogen solution. So again, that comes down to vehicles and OEMs and supporting the market. And then finally, I think people have been saying about, taking out or minimizing risk and developing knowledge and experience and evidence. I'm a real believer in learning by doing. So I think demonstration is important. I've touched on things like the purity piece. I think we need to move quickly to scale where we can actually have cost discovery and find the most appropriate solutions. And if I picked a sector to focus on in transport, it would be the heavier end, the HGVs, for the reasons we've discussed about the size of the market and the demand. So there were three things there: demonstration, pricing, and integrated hydrogen strategy.
Thanks, David. And Phil, you said that RWE are supportive of both blue and green hydrogen. So what's your perspective on policy to enable hydrogen use in the power sector?
Well, I sort of agree straight away with the most important point the other two people raised, which was is the commercials, follow the money. We're talking about a big increase in the cost of hydrogen, potentially. Of course, it depends on the business models for the supply end. I think BEIS are focused on this, creating the supply end. I think that's where we may well see their policies coming forward. I don't know if that means that the gas that goes into the network is effectively at a similar sort of cost to natural gas, because effectively the incentives are on the supply end, and therefore they then reflected into the overall cost of natural gas consumers. But the commercial bit definitely is a really important piece. I know there's work at BEIS on the business models, and I sit on two of those groups to bring that forward. So I think that's really important. You don't want, hydrogen into our power plants is going to reduce the CO2, so you want them to run. You don't want them to run less than plants that, shall we say, slightly higher CO2. I think there needs to be a regulatory framework for the transportation and storage. So all the safety issues, all the stuff needs to be done as well. That's a clear piece of work that helps create hydrogen. I think in the commercials, as I say, the deblending costs are very high. When I read £1 a kilogram, I read £50 a megawatt hour added to the cost of the wholesale price of electricity. So that's more than the cost of deblending is more than the cost of production at the moment alone, without the blue hydrogen. And then in terms of hydrogen, we are green and blue. We're quite happy to take whatever form of hydrogen. Obviously, the commercials aside, we're more focused from the supply end on green hydrogen rather than blue. But we're fully supportive of hydrogen going forward. Our business, we've got a commitment to be net zero by 2040, and therefore, hydrogen has to be a big part of that. And then in terms of green hydrogen, again, I'm sort of just directly connected wind turbines. I know some things like the RTFO requires that at the moment to qualify. We can see a lot of benefit in things like guarantees of origin, so you can use the power from wind farms and not necessarily be directly connected. We think that's really important. We think green hydrogen, I agree with the previous comment as well about blue and green. Hydrogen blue comes first and green. And another reason why we're not colorblind is because we recognise that firm, flexible generation of hydrogen is essential to go alongside perhaps the more potentially intermittent renewable hydrogen in the form of green hydrogen. So the two need to work hand in hand. There's mutual benefit in the two different forms of hydrogen. Does that sort of answer the question in a long-winded way?
It certainly does. Thank you, Phil. And I think positive to end on a point of consensus in terms of the need for policy to support those commercial answers, but also for industry to work on that as well. So many thanks for your comments and questions that came in there. And again, thank you to the presenters on those use cases. We're now going to move on to our Ask the Audience part of the webinar. So again, really keen to hear from those of you on the line. Fingers on buzzers, please, via Slido. We've got 3 questions coming up now. Now, for the first of these 2, we've set you a little challenge. We want you to answer in as fewer words as possible. So channeling that Friday feeling. Let's first bring up the question. Yes. So as you can see on the screen here, what are the benefits of deblending? So thinking about what you've heard today and your own understanding, can you set out to us in a few words what you see as the benefits of deblending? So we're seeing lots of answers come in. So flexibility is certainly a key here. Picking up some of the points we were discussing in terms of being able to accelerate the transition, accelerate hydrogen uptake. Interesting that it's also picking up some of the presentations and the points made in terms of providing efficiency or optimization for the network. Flexibility is very clearly a winner currently, as the comments are still coming in. Inclusive transition is a point that's been made a couple of times. That's growing in prominence as a clear benefit of deblending. So perhaps to bring in some of our speakers from earlier, Tony, it's clear from those who are on the line that flexibility is a clear benefit of deblending. I think that would chime with National Grid's consideration and work to date on deblending.
Yeah, absolutely. I mean, I think that's why we set the challenge in the first place, and why Costain responded in the way they did at the outset of all of this. It does provide some options. There are costs. There's costs with everything, but it's a tool in the arsenal that we're working on here. We're not saying that deblending is the way forward. It's one of the options. We could be doing blend only. We could be doing a step-by-step conversion, pipe by pipe, to 100% hydrogen. But if it does work at scale and at a cost that we can tolerate, as you say, it does give us the flexibility.
Yeah, and I think that reflects the optionality comment as well.
And just picking up on that point, it may well be that one size doesn't fit all, and different parts of the country transfer at a different rate using different methods. So it may be that Deblend just has a few uses for a few assets in the country. Who knows at this point? You know, we're very, very early on in just really flexing what is there to test the options.
Yeah, I think that's an interesting point, and was certainly one of the conclusions of the Pathways to Net Zero report, that that scenario of 2050 might be quite different from today in terms of being a more fragmented or regionalized system. And as you say, deblending presents a new range of options which might lead to differences around the country. So another point that's coming up quite strongly in the comments is, or the voting, is reducing the transition risk. And again, I think that links to the optionality point.
Yeah, and I think that's an interesting one, because if we start creating hydrogen in the country, the more that we can actually take onto the network without introducing any risk in the network, it's a safer conversion as we're going, and it promotes hydrogen to come onto the network. As we've already seen, we're going to need a lot of hydrogen. So the worst thing possible would be to say we want it, we want it, we want it, and then say we can't take it. So if we've got Deblend that we can control things, that would certainly de-risk transition.
Okay, let's move on to the next question that we have for you all. So the second question here is, what are the challenges that you see with deblending? So again, if possible, just a word or a few words to describe what you see as the main challenges from what you know and from what you've heard today. Cost. So cost certainly seems to be the biggest factor. Issues of purity and gas quality. Lack of laws and regulation is perhaps something that we haven't touched on to too great an extent. Would there be specific issues there in relation to deblending, or is that part of the wider consideration of new regulation and legislation that might be required for the role of gas going into the future?
Yeah, I think that's an interesting one, because we are, if we're going to be doing deblending, we are entering a processing phase of the gas, and I'm sure we're going to have a look at what our license says, and it will probably challenge some aspects. So I think there are some more legal aspects that we would need to look at as we roll out hydrogen anyway. And actually, are the boundaries that we see in the current structure the right ones? It may need some movement of the boundaries.
And a similar point in terms of a sort of a peripheral but important issue to some of the technological issues or technical issues we've been discussing today is the business models, or how deblending would be priced, and the role of sort of consumers paying for that. Is that something that's been thought about?
Not at this point, and you know, from our point of view, we are very much looking at the technical aspects with it. We would then have to engage with the wider market to look at the cost aspect and how that would be distributed, and how it would be rolled out ultimately, because there would be quite a sizable cost to introduce the facility. But if it's only supporting the rollout, as Lloyd sort of described at the start there, you put a deblend facility in to almost protect some assets as you bring hydrogen to them. Once that area gets up to 100% hydrogen, your deblend assets are no longer needed. So is there a concept whereby you move those facilities downstream so that you convert as you go, and you actually reutilize those facilities so you don't end up with a stranded asset from a CapEx point of view? Could actually support some of Lorman's comments about, you know, standardizing the build, and could we skid mount it or move it around in that sense? Just some ideas there.
And I think that's interesting to think about the long-term cost profile, where perhaps there's those additional costs for a certain period of time until there is 100% hydrogen in parts or all of the network, and a further exercise to map how that cost profile changes over time would be something to address the point that most people have identified as the challenge there in terms of cost. As you say, that's going to be different at different points of the pathway. I think that's all the responses coming in. It seems to have, oh, one more. It seems to be hovering around the 30 mark. Many thanks for that. That's it's really important to us to get interaction and engagement on this issue, and to understand benefits and challenges that those of you on the line see. That can certainly help influence our further thinking and work done to address some of these issues. The third question that we wanted your thoughts on, if we can bring that up on the screen, is other opportunities. So you're no longer bound to your 3 words or less. You can use as many words as you want. We're really keen to understand what other opportunities you think the networks need to consider in relation to deblending. As I said, this might be helpful in indicating future work or future directions for work on deblending to take, thinking about other areas to link up with other network work that's going on. So a first opportunity, maybe something to discuss while some other comments are being typed in. So how can you guarantee you get the hydrogen to where it needs to go? Tony, Lloyd, is that something that you've thought of or considered in work to date?
That was sort of what I alluded to in the next steps of the project, which is looking at modelling how this might work on the actual network. But it's a very complex system, so there's a lot of work done to manage gas quality and movement on the network at the moment. So trying to transition that knowledge and experience into how we manage hydrogen on the network is going to be quite interesting.
Thanks. I think that comment on the top there in terms of working to standardize the process to reduce costs, reproducibility, yeah. Matching deblend with CCGT needs, point there. Oh, getting lots of comments now. Safety confidence, certainly a paramount issue. These are actually disappearing off my screen. Who carries liabilities? We were mentioning the legal issues and related issues to that. Standards and legislation.
Yeah, some really good feedback here, and it's a shame they're dropping off the bottom of the screen, but this is exactly what we're looking for, is what haven't we looked at that we really need to consider? We can go back up the screen.
Yeah, right. I was confident they weren't lost, but
I think that point about the biggest opportunity is to minimise the amount of deblending is a really important one. As we've seen, this is one tool in the potential arsenal. If it is expensive, you only want to be using it very frugally. So I think that's a really good point. Unless there's some very, very clever person out there that can figure out how to do this much, much cheaper.
And please do come forward if you're on the line.
I'm all ears. Yeah.
Okay, well, just to echo Tony's comment there, this is really valuable comments and much appreciated. So certainly following today, we'll take those comments on board and keep you all updated on further work in this space. And on that issue, that's actually where I want to move on to next. So continuing with our theme of sort of opportunities and to discuss some of the ongoing work and gas network projects that link to deblending. We're now going to hear from 3 more speakers to discuss the Future Grid project. We're going to hear from Tom Neal, Mark Danter on the H21 microgrid, and Nancy Thompson on LTS futures. So Tom, I think it's over to you.
Thanks, Tom. So we've just got one slide if Katie can move through. So I think really what we wanted to do in this section is just to sort of summarize some of the key work that's going on with the networks at the moment, and picking up on the point about the coordination. It's interesting that there's interactions between all 3 of these projects in different ways. So try not to steal the thunder from the next 2 speakers who have some interaction with this. I just wanted to give a bit of an overview of the Future Grid project that we're currently developing. So it's an ambitious program of work that's seeking to build a hydrogen test facility, an offline facility, using decommissioned assets from the NTS, the National Transmission System, and that's up at DMV's Spade Adam facility in Cumbria. So it's actually building on some facilities that H21 are developing and that Mark will tell you about just after me. And we're looking at this to be able to allow us to have a facility where we can test hydrogen alongside a number of our key assets and look at blends of sort of 2, 20 and 100% to look at the impacts they have on the network. But actually what that is doing is providing us with a platform then to start to develop further testing and trialing. So as you can see, sort of we've got a planning phase going on at the moment, the pathway to Future Grid, and we're currently working on an NIC, a Network Innovation Competition bid, which is our phase 1 to build the test facility. But as part of the programme, phases 2 and 3 look at actually expanding out the potential of this test rig to allow, importantly in sort of phase 2, deblending trials to be considered. So the work that we've done to date, as you can see, and a number of the questions and challenges that we have, very much looking at the opportunity to look at some testing of those different technologies to tackle some of those problems and some of those issues, as well as looking at the impact of hydrogen with operating compressors. And then more widely, actually, this rig, and I think you'll see from the talk that Mark will give you shortly around the H21 facilities as well, combined provides us with an opportunity potentially to have a representation of the UK gas network in an offline facility, allowing us to test more assets, more technologies, and challenge more issues that we may have in sort of transitioning over to hydrogen. So it's a really exciting space and sort of a real good opportunity that's facilitating potentially more work and more opportunities. So as I said, at the moment, we're very much on the on the sort of bid for the first phase to build a facility, but very much where we're looking at the moment as to where phase 2 and 3 could take us, and the outputs from today are absolutely fantastic in helping to inform that. That's all I really wanted to sort of say on that one, Tom. So whether we're passing straight on to Mark for H21.
Yes, please, straight over to Mark.
Okay, thanks, Tom and Tom. Just want to touch on 2 of the projects we've got ongoing with H21. Obviously, there's a suite of things we're managing in terms of the blending and the 100% hydrogen. So if you move on to the first slide, please. So as part of the HyDeploy 2 project, which is building on what's been developed and trialing at Kiel, we've got the first live network trials for the 20% blend, which we're running out of the Low Thornley site up at Gateshead, which has been touched on earlier. And that is part of a bigger overall plan that's been implemented and managed by Keith Owen, who spoke earlier, the integral site. So that's working with ourselves, Northern Power Grid, Northumbrian Water 3 and Newcastle Uni. But we're also looking at the first step of trying to get an insight into using and touching and feeling the appliances. So we've in the planning process of having 2 semi-detached houses built up at Low Thornley, and we've been speaking with the various appliance manufacturers for fires, cookers, boilers, as well as the new hydrogen flow meters. So that's proposed to hopefully be built by the end of this year, 2020. We're also looking at the Spade Adam site as well. So if you want to move on to the next slide, please. So up Spade Adam, we've already had some work commence as part of our phase 1. Keith touched on it in his presentation in terms of the consequence testing, which is used to inform the QRA. We are just at the start of construction of our phase 2, which is an NIC funded project, which is looking at network operations. So to commence that work, we engaged with HSE. They reviewed 700 plus of the network procedures for operations and maintenance. And we're just finalising a master test plan that will be used to develop and control the tests that we've got planned for on the microgrid, as Tom mentioned. So appreciate it's quite a small picture in front of you, but in the distance, just behind where it says demo grid, those are the 3 houses that DNV built as part of our phase 1, and we're planning to fit some appliances in those. Under the phase 2, where it says demo grid, we're planning to replicate the various pressure tiers and configurations we've got in the distribution network. So the medium pressure, intermediate pressure, and low pressure. And as you can see, we've got a control building area. We'll be managing all the testing. We've got a HP reservoir, which National Grid have kindly donated some high pressure pipe that we're using as storage bullets. And we're just, the idea is we're trying to replicate the various operations and maintenance procedures that we use, and seeing if we can do that in a similar way with hydrogen, such as purging, venting, flow stopping techniques, bagging off. We can do new connections, as well as other things like, can we still use the same tools, the PPE, and all that work will also inform the training that's going to be required for our next intermediate phase, which is an unoccupied trial on part of the grid which we've luckily managed to secure a part of an abandoned part of the network down near Redcar, Middlesbrough. As Tom's alluded to, the idea is we've on with construction this year, with testing commencing back end of this year, mid through to mid 2021. The plan is that the future grid NG building would then link into that, so that we can have, as Tom said, an end-to-end mock network that we've got from injecting the natural gas through to using it at the homes. All this work, to give a bit of a picture, is all coordinated across all the networks. So all 4 GDNs and National Grid are part of our Phase 2 H21 project. And there's a number of groups that have been set up with bays, and all the networks have representatives on that. It's helping us move forward to the next phase, which is Phase 3 of our project, which is the live trials. And we're hoping, as part of this, is to gain all the evidence required for the safety case. Okay, I'll hand over to I'm not sure it's Nancy or Joe.
Hello, Nancy's on.
Hi, Nancy.
Okay, are you ready? Should I just go ahead?
Yes, please do. Thanks, Nancy.
Okay, hi, I'm Nancy Thompson. I'm from SGN. Sorry, I've only just joined. I don't actually work Friday, so I've just said doing this as a favour. So sorry if I do any repetition from what's already happened already this morning. I'm just going to talk about the future of the LTS, the projects that we've been doing and hoping to do in the future. I've worked for SGN for nearly 4 years now, and my background is a pipeline integrity engineer on high pressure transmission pipelines. So this project was kicked off actually when I was on maternity leave, and it looks at repurposing the LTS network. So that's everything higher than 7 bar for SGN. So and that's for Scotland and for the southern networks. It was sorry, I'm just trying to find my notes. So it was the first exercise was a desktop exercise with HSL to assess the scientific and regulatory feasibility of repurposing the LTS for hydrogen and CO2. So the scope didn't include PRSs, it was just pipelines itself. We've actually got a mothball pipeline, the Granton to Grangemouth pipeline, which we asked HSL to also do a case study on, and they also did a couple of other pipelines that were similar age, similar grade, similar wall thickness, to see, what further work, all the gaps that they'd identified in the literature review and how they would apply to actual pipelines in the real life scenario. So the first phase has shown that further testing needs to be done and further work, but a significant percent of the SGN LTS network consists of relatively low strength pipeline grade, operate a low stress and could be repurposed for hydrogen. Obviously, integrity assessments and risk assessments and further testing is required, but it's looking like a large percent of our network is going to be able to be repurposed. That this is, if you were to build a hydrogen pipeline today, it would look similar to an LTS pipe. So we held a workshop in February with all the other GDNs, National Grid, HSE, BAYS were there, and some subject matter experts as well, some pipeline experts. So this is just to really share the knowledge, and so also Lloyd Mitchell was there and presented on the work that National Grid have been doing. So we're sharing the knowledge, identifying the gaps that we'd already identified in both the work that NHS and the NTS had been done and also on the LTS, and then exploring any other gaps in the workshops. So then we compiled, if we could go, sorry, to the next slide. Yeah, so then we come, oh no, not that, so just the one before, the one with the gaps on. yeah, that one. So we compiled all the gaps together into like work packages. So this is with like material where there was gaps that we obviously missed in the pressure reduction stations because that wasn't part of the scope, inspection, maintenance and repair, and also the QRA. So if you were the material work package is by far the biggest. So there's quite a lot of overlap with these work packages. So if I just were to give you an example now of something like if you wanted to understand the effect that hydrogen has on an acceptance criteria, so that could be like a 6% dent or 80% wall thickness for like low stress pipelines and how it affects P11. So that's all understanding how the hydrogen how the hydrogen diffuses into the metal and could potentially cause hydrogen embrittlement. So could then affect the we also know that when we have to inspect the pipeline that there's going to be an increased flow rate, so that could have the effect on the speed of the pig and how defects can be detected. And then also at the moment there's no option for a live repair on a hydrogen pipeline, so we'd need to do some further testing on what live repairs can be done or what live repair options are there for hydrogen pipelines. And the reason for this is just due to the increased risk of an ignition of hydrogen if hydrogen is released. So it was kind of just to show this slide to show you how all the gaps and work packages that we've pulled together, how they all overlap and how we need to do the work together, like simultaneously and collaboratively. So if you just want to go to the next slide. So we set up the iGEM LTS Futures Group, which all the GDNs and National Grid are members of. And this is where we started off doing some work. So this is looking at repurposing, or the change of use and the repurposing of the TD1 standards and TD13 standards. But really, the next phase is designed to develop the safety and technical practical evidence that we need to support the use of hydrogen in the LTS and the NTS. So the work packages that we've proposed, these really underpin many aspects of decarbonising the pathway, because it'll feed into the network safety and impact that will provide the evidence for 2023, securing the NTS and LTS assets, providing technical input to ensure when we try to decarbonise that decarbonisation of industrial clusters can be delivered, what the role of the LTS and NTS is in the system transformation, and also how that has an impact on the hydrogen rollout and also the green recovery. And then if you could go to the next slide.
Nancy, sorry.
Sorry.
Just conscious of time. And
yeah, sorry.
That's we've overrun. So I'm just going to intervene here to begin to wrap up the session. But many thanks. And as I said, it was my fault that things overran there. Just to thank Tom, Mark and Nancy for those really useful overviews of some of the network projects underway that link to and will take forward that blending that we were speaking about. Before I pass to Tony to wrap up, I'd just like to thank all the speakers and to all of you on the line for your comments and questions. Many thanks for joining us today, and over to Tony.
Yeah, just quickly, because I'm very conscious of time and many of you will have to go off to other meetings. Just echo my thanks for everybody joining us. I will just stress Deblend is one option that we're working on here, so it's really good that we're able to actually share this with you and get your feedback. We've heard from all parts of the market for various needs. We've heard from offshore looking at the existing capability out there. We've identified cost and scale as an issue, so I'm all ears if people have got ideas to decost and standardise this. Let's see if we can innovate and come up with some good solutions. What my key takeaway, which a number of people highlighted, was the need for hydrogen to prove these use cases and technology. We need lots of it, and we need it soon. I guess most fundamentally, I didn't hear of any showstoppers through the conversation that we've had today. So that's good news. So thank you very much for joining us. The slides will be available afterwards, and there will be a recording of the session available as well. So thanks, everybody, and see you soon. Thanks.
Thank you. Thank you.